Okay, we continue the lecture. Okay, here you have some examples of polarized carbon bonds. Here you have why they are polarized. This is the electronegative each atom. As you can see, carbon is 2.5. All the atoms that are on his right are higher electronegativity. Remember, electronegativity is increasing to the right and is decreasing going down. Okay? Basically, a polar reaction is the reaction between electron-rich sites with electron-poor sites. The curved arrow is going from the pair of electrons to the carbocation or a cation. Okay? The two pair of electrons that are moving from B to A is the ones that are forming the new carbon-carbon or carbon heterocycle bond. Some nucleophiles can also be electrophiles. You can see some examples here. Okay, because normally they are Lewis acid and Lewis base. For example, here you can see that the carbonyl group can be electrophile in the carbon is electrophile, but also can be nucleophile on the oxygen. Okay. Here you have some exercises that you can do at home. Okay, we did it in the lecture room, and you can identify nucleophiles and electrophiles. Okay, we can put an example of a polar reaction. Basically, we will do the addition of hydrobromic acid to ethylene. Okay, here we have ethylene. Here we have hydrogen bromide. And what is happening? Okay, if we go slowly, we have this pair of electrons that are forming the double bond. These pair of electrons that are forming the double bond are quite nucleophile. Okay, the first step is always the pair of electrons that are forming the double bond is attacking the proton. Okay, and at the same time we are breaking the hydrogen bromide bond. Remember, because it's polar, the two electrons are going to the bromine. And what we generate is this carbocation. We add the hydrogen here in this carbon, and we generate a carbocation here because we are losing one electron now. And we generate as a counterpart, as a bi-side product, bromide negative. Okay, this bromide takes these two electrons, becomes bromide negative. Okay, this is the intermediate. Okay, here we generate an intermediate that is a carbocation. What is the difference between an intermediate and a transition state? Transition state is basically something that we cannot isolate, and the transition state is something that we can isolate. Okay, transition state is a maximum of energy in the diagram, and intermediate is a minimum of energy. Okay, when the bromine attacks the carbocation intermediate, because it's negative and we have a positive here, that means the negative will attack the positive, we generate the bromoethane, that is our final product. Okay? There are some rules to use curved arrows in polar reaction mechanism. The more important rule is that the thing that is moving are electrons. Okay, the electrons are jumping from a nucleophilic source to an electrophilic sink. For example, we have oxygen here, this pair of electrons are jumping. This nitrogen, this pair of electrons are jumping. This carbon negative, this pair of electrons are jumping. This double bond, this pair of electrons of the double bond are jumping. Okay? And just the opposite. The nucleophile, this pair of electrons are jumping to the carbocation that has a free orbital. Exactly the same here. here the nucleophile attacks the carbon, and at the same time, because the carbon cannot break the octet, we break this bond. That means we are forming this bond at the same time that we are breaking the carbon-halogen bond. Or the nucleophile can attack a proton and then we break this hydrogen-oxygen bond. Or, if we are using double bonds, the nucleophile attacks the carbon has a density positive charge. Okay, this attacks here, and then the double bond between the carbon and the oxygen are going to the oxygen. The most important is don't break the octet. Rule number 2, the nucleophile doesn't need to be negative. Could be negatively charged or neutral. The only that he needs is a pair of electrons, a free pair of electrons, doesn't need anything else. Okay, the pair of electrons can be like here, charged, that is methoxide, but also a methanol, that is a pair of electrons without any charge, can attack a nucleophile. Okay, obviously this will be a stronger nucleophile than not this. And another example of neutral is the double bond. The double bond attacks the hydrogen bromide, okay, and is neutral. And what we generate is a carbocation intermediate. And also the electrophile can be either positive charged or neutral. That means in this case, the double bond is attacking a water, protonated water. That means that it's taking the proton, we break the hydrogen-oxygen bond, okay, and we generate the same carbocation than before and neutral water. Exactly the same, well, not the same, but for example, the double bond can attack a hydrobromic acid, hydrobromine, okay, and again we generate the carbocation intermediate and we generate the bromine, in this case bromide, negatively charged. And rule number 4, the octet must be followed. In any case you can break the octet, not with hydrogens, not with carbons. Okay, we talk a lot about this rule. Okay, then we can describe a reaction based in his equilibria, rates, and energy change. Normally the reactions are reversible. That means we have starting materials and we have final products. And this process is reversible. That means that we can go from starting materials to final products and to final products to starting materials. If the reaction is reversible, we can determine the equilibria. That means in a determined condition, how much starting material and how much final product we will form. We define the constant of equilibrium like the concentration of the final products divided by the concentration of the starting materials. Here you have an example. For example, ethylene plus hydrobromine. We saw that we get bromoethane. If we calculate the constant of equilibrium, will be bromoethane divided by the concentration of the starting material, that will be ethylene plus hydrogen bromide. And if we calculate this in standard conditions, we get that the constant of equilibrium is 7.1 multiplied by 10 at 7. That means that it's very well displaced to the final products. We can define the Gibbs free energy change, that is the Gibbs free energy of the product minus the Gibbs free energy of the reactants. Okay, and we define the standard free energy change for a reaction as variation of G standard, that is 25 degrees, 1 atmosphere, and pH 7. Then we can define that one reaction is exergonic when the variation of Gibbs is negative. Okay, we are giving energy to the system, exergonic, exothermic reactions normally. And we can define that one reaction is endergonic when we need to give energy to the system. That means that the Gibbs energy of the reactants is less than the Gibbs energy of the final products. If we define the variation of Gibbs standard like minus a constant multiplied by temperature multiplied by the Neparian logarithms of the constant of equilibrium, we can arrive to this formula, where R is this constant, the temperature always has to be in kelvins, E is 2.7 more or less, and Neparian logarithms of K8 is the natural logarithms of Kf equilibrium. Okay. The Gibbs standard reaction, the Gibbs standard energy, is depending of two factors. One is of the variation of enthalpy of the reaction, that is variation of H, and the other factor is the variation of entropy. Entropy basically is a grade of disorder of the system. Okay, when more disorder, more entropy. Normally, the important factor in these reactions is the enthalpy factor, the heat factor, not the entropy. Okay, here you can see that for the reaction that we studied before, the polar addition of a double bond to hydrobromic acid, the variation of Gibbs is minus 44, variation of enthalpy is minus 84, variation of entropy is 0.132. And the constant of equilibrium, as we said before, is 7.1 to 10 at 7. The process is exothermic because obviously K, the equilibrium is major than 1, that means that we will have more product than not static materials, and the variation of Gibbs of the reaction is negative, that means exothermic. Okay, you can do this exercise. Then, what is the diagram of the energy? Okay, well, when we described this reaction, we saw that the first step is the addition of the double bond to the hydrogen and breaking of the hydrogen bromide bond to form this carbocation intermediate. In a second step, the bromine attacks the carbocation and forms the final product. Here you can see the reaction coordinate. We start the reaction. Okay? This double bond attacks this hydrogen. We increase the energy in order to favor the attack. And we arrive at transition state. That is when these pair of electrons attach the proton and are forming this bond, and this bond, other bond is breaking. Then this happens, and we arrive to the intermediate. That has to be a minimum. Remember that intermediates are a minimum of energy. This is the carbocation intermediate. Okay, don't take care about the size, about the how big are the figures. This is the less important. Okay, if we do this reaction, we have the activation energy. The activation energy is the energy that we have to give to a reaction in order to work. Okay, it's based in kinetics. It's always higher than the variation energy between the reactants and the intermediate, because this is based not in kinetics, in thermodynamics. That means this is the energy that we have to work. This is what makes that a reaction is fast or slow. When higher is this energy, more slower is the reaction. Then we go for the second step. We have here, and the reaction progresses, the carbocation, the bromine is attacking the carbocation, and we generate the final product. This can make different variations of G. For example, here the variation of G regarding the starting material, the intermediate is this, here is this, here is this, here is this. If we do this reaction, what we have is, we start with the double bond attacks the hydrogen, we increase the energy, we arrive to a transition state, that is when we are forming the carbon-hydrogen, we are forming the carbon-hydrogen bond and we are destroying the hydrogen-bromide bond at the same time. And then, when this happens, we generate the intermediate, that is a carbocation, that is a minimum of energy. Remember, transition state, always maximum of energy, intermediate, minimum of energy. Once we have this, basically the bromine attacks, we get an intermediate, we get a transition state, not intermediate, transition state, that is a maximum of energy, that is when we are forming the carbon-bromine bond. Once it's starting forming, we are losing energy, until we arrive to the final products. Important things, what is the energy activation? The energy activation is always between the starting materials and the bigger transition state. Yeah, which is the right transition state? I mean, which is the step that is important? Always the one that has the energy activation higher. For example, this energy activation is higher than this. That means that the most important will be this step. This step will determine how fast is the reaction. If we are talking of thermodynamics, what we are talking? Okay, the thermodynamics is basically starting materials and final products. If final products has less energy than starting materials, the variation of Gibbs will be negative. If it's negative, then will be exorganic. If the opposite, the final products are more energetic than not the starting materials, means that the variation of Gibbs will be positive, will be endorganic. Okay? Then, how are working the reactions? Well, normally the reactions has a higher activation energy, has a very high activation energy. That means that if we want to do a reaction, normally what we use as a catalyst is what happens in our body. Okay, we eat something and we degrade this in order to form energy. But we are not doing it by burning, because simply the energy activation of burning is so high. What we are doing is dividing this process in several intermediates that have an activation energy by far lower. Here you can see that these reactions are the same reaction, only that one is happening in one step and the other is happening in several steps. Normally the one step is uncatalyzed and has an energy activation that is huge, while the enzyme catalyzed reaction is happening in several steps and the energy activation is very low compared with the first one. Okay, this is why it's working in our body. Okay, here you have study questions, reading assignment, and thank you very much for your attention, and see you soon.